Hi, I'm Andrew Haugen.
I'm Lucas Lassila.
I'm Zeph.
And for our 320 Electronics 2 final project, we decided that we would tackle creating an electric guitar overdrive pedal. Guitar pedals are circuits that lie between the signal path from an electric guitar and an amplifier and allow the user to exert some control over some sort of effect. An overdrive pedal deals with distortion, a low-level form of distortion called overdrive. It allows the user to have control over gain that would alter the sound by introducing clipping and harmonics to create a musically desirable but still raw and gritty sound that's usually heard in genres like punk, metal, and rock. So we decided that since this is a relatively standard device used in music, we would follow industry standard procedure for this. The first thing that we decided to do is use a 9-volt battery. That is standard, all pedals use 9-volt, whether a wall socket or a battery, and we created a voltage divider so that we could change the 9-volt DC and create an artificial ground that would allow us to have positive and negative 4.5 volts to allow the AC signal to swing around. And we use this to both power the circuit and bias 2 of our op amps here and here. While the third op amp did not require any biasing, the setup of our circuit was that between the input and output jacks, we would have our gain stage first, allowing user input over the gain and distortion, our tone stage second, allowing a user control over the envelope of some kind, a simple potentiometer for volume, and then just a voltage follower configuration op amp to act as an output buffer. Here is the schematic we designed. As you can see, there is our voltage divider circuit where the battery would be connected. And then between our 2 guitar jacks, we have coupling capacitors to help with noise and DC. We have biasing going into our op amps, and then we have our gain stage, our tone stage, our voltage follower output buffer, and then a filter here and our volume control there.
So for our gain and clipping stage, as you can see here, if we look at it from the time domain, we have a non-inverting amplifier and it runs through these 2 clipping diodes as well as some nominal gain. These clipping diodes are actually what produces this distorted effect that is so common in the overdrive pedals, which is cutting out the top ends and holding the top ends of a signal constant. Now in the frequency domain, as you can see in the prior slide, we had a low pass and a high pass filter. Now this creates what is a band pass filter, and it is primarily towards the higher ranges of the guitar's frequencies. Now by adjusting the potentiometer in that overdrive pedal, we can see that a higher level will lower the gain for all signals, but also filter out that bass a lot more. And as you lower that, you'll see that this brighter end, or more so the higher frequency spectra, gets a lot more gain, while the bass frequencies get much less. Now, based on our references, this is a half Baxendal filter. The Baxendal filter is a active filter that allows someone to, through RC circuitry, control the bass and the treble of their output. Now for ours, it only controls the treble, which appears as basically what is a low-pass filter, with this variable resistor up here making that roll-off either steeper or shallower. Now you can see that here with a lower resistor setting. This roll-off is a lot steeper, and any high-end treble will go cut off a lot more, while turning it up a lot more will have a much shallower roll-off.
So here we can see our implementation of the circuitry in EECE PCB layout. A couple things to note here is the use of Manhattan-style traces. So this allows us to increase the amount of ground pour in our circuit. We have here our first stage, which is our overdrive stage, associated potentiometer. Our second stage here, which is our tone stage and associated potentiometer. And finally here we have our potentiometer and circuitry for the level stage and our buffer op amp. Here we have our input and output jacks, and likewise their test probes here, and of course our battery. So, for the results, the overdrive and the tone functions are great. They are adjustable and allow the user to adjust the overdrive naturally and the amount of treble in the output signal, and they provide a nice sound. The 9-volt power supply circuit works well and not only biases the circuit as intended, but also consistently powers the op amps. Unfortunately, the level circuitry was not so successful. The RC filter formed by combining the capacitor and the potentiometer attenuated much of the output signal and also failed to block the DC bias of the signal. This is not a big problem. Guitar amps are designed to handle this, but nonetheless, it is out of the design constraints. So again, here we can see our overdrive stage as Zeph talked about here. And this is an example from the Ibanez Tube Screamer, which is considered to be one of the founding overdrive pedals and referenced in the industry a lot. Naturally, they have a similar curve, similar style band pass. Ours has a little more gain, a little more linear spacing of the curves based on potentiometer, but regardless, positive result. Likewise with the tone, here is an example of the half band pass, half Baxendale style filter, and ours here. So naturally, increasing the gain here for brighter frequency, brighter tones, brighter sound. Same thing's happening here. Again, a positive result. On the bench, testing with 1,000 hertz signal, 1 volt peak to peak. You can see our input here, we have our output here, and first stage, the clipping stage, you can see that we have clipped our input signal, and that's great, off to a great start. See here on the tone, so 1,000 hertz, that's in the upper range with the center control. You would expect some attenuation here, a little bit of distortion added again, but we are keeping our signal integrity. That's really good. Finally, on the output stage here, we can see not so much. The very minimal signal amplitude being passed, a lot of fuzz on there, and it is at its DC bias of 3 volts. This was how we knew something was going on in our final stage. As you can see here, this is the filter that causes flows on the test bench, and although these values should provide us with a very low cutoff frequency for a high pass filter, that proved to not be the case. So to get around that, we just added a little jumper wire here, just to circumnavigate this section of the circuit here, so we could test our first two stages. In addition to these challenges, we also had a lot of learning to do when it came to designing such complicated RC circuits with feedbacks on the op amp. That was new for us, and doing analysis on that was a new challenge. We did have a couple hiccups with the PCB. You can see here, just barely this little wire. We did miss a trace on our biasing network. Found that during testing. Quick wire, no problem. And naturally, just learning how to kind of troubleshoot a board here. It took a couple of tries to figure out what things to check and in what order.
All right, and for our acknowledgements here, all these references are primarily based from hobbyists. These last two were primarily used for the schematic, and this top one was used for figures.